Welcome everyone to SAIEE Load Research Chapter. My name is Marcus Dekener. I'm Chair of the SAIEE LRC and will be helping run this session. The speakers in this presentation will be presenting work done to evaluate shifting the South African national load profile with residential water heaters. I will give you a rundown of the talk we are about to have. As part of the load shedding we have had over recent years, obviously the question on everyone's lips was what domestic load on the grid can be shed in some managed way to lessen the demand on the grid, thus giving us less load shedding. I think a number of studies, at least 3 of them, were launched, and a further one which is partially related was launched on the Eskom side with smart meter technology to say what are the things that we can switch off and what are the ways we can switch them off to relieve pressure on generation on our grid. I was fortunate enough to have been joined to the team which is now going to talk about the simulations that were done and came to respect the work they did very much. Today I asked Jesse and Ken to focus on the simulation and the related techniques and to give it good treatment, because to my mind it's a very good diagnostic tool to help us right now and in the future to diagnose demand on network and figure out what are the interventions on the demand that can help us get through our periods of difficulty. The work that you're going to see now was presented in 2024 to Workstream 5 of NECOM. That's the DSM and energy efficiency stream. I'll just talk about Jess and Ken. Jessie is an academic at Wits University where she's got over 10 years experience in research. Her doctoral thesis was on the exact topic that we're talking about now, on the simulation of hot water geyser loads. So there's not much about it that she doesn't know. And Jessie went from thermal simulations to calibration in a lab and then folded that up into the expected demand at network level. So if you ever wanted to know something about simulation of thermal systems, Jessie's the person that can tell you that. Now also hidden behind this work is a guy called Ken Nixon who made Jessie's dreams come true with a computing cluster at Wits University. Ken knows how to make these things work and you'll see why. Ken is an associate professor in Wits School of Electrical and Information Engineering and has got over 25 years experience, a string of PhDs and MSCs via him and still with him, and he has rather broad interests. You can engage Ken on earthing and lightning as well, high voltage engineering, energy systems, high performance computing, computer as well as information and software engineering. Interestingly, Ken can do quantum computing and can even give you courses in it. So without further ado, thanks and welcome Jess and Ken. When you start talking, please put your video on. The floor is yours. Please go ahead.
Thank you, Marcus. I think I need to load my presentation again, so give me a moment. Thank you, Ken. Thank you, Marcus, for the wonderful introduction. And thank you to the Load Research Chapter for the invitation to present this work. We've named this Shifting the National Load Profile, given the idea that we really wanted to see what water heaters could do to shift that national load and ultimately, in some claims, end load shedding to some extent. So we really wanted to tackle that. As a note, I'm from Wits University with Ken, who's also an academic at Wits University. This was a project that was funded by USAID and in partnership with the US Department of Energy and the DMRE and Berkeley Lab. So thank you for your attention on this, and hopefully we have some answers around this question. Right, so just a quick overview of this presentation. We're going to talk about water heaters in the grid. If some of you are not very aware, we're going to talk about what it means to have demand flexibility and how all the distributed loads add up to something quite significant. I'll talk to you, as Marcus had mentioned, about the horizontal oriented geyser model that I produced as part of my PhD, and how we used that to build up for the national profile using a population study. Ken will then move on to talking about the national load, the load profile. We'll look at baselines for 2023 and 2033. So that's if nothing happens, if no interventions happen, this is the natural course of things in the next 10 years. And then we will look at simulation impacts. So what happens if we make any changes from a policy level? So, and we'll talk about those interventions in a moment. But ultimately, we're simulating what that might look like and what kind of effect that would have on the grid. And we'll just have some concluding remarks. Right. So I wanted to start off with a bit of a provocative title, which is Turn Off People's Geysers to Keep the Lights On. And I think that was a proposition that was made and gained quite a lot of media attention at the time. I think we're all very much aware of load shedding, and I think one of the participants has mentioned, Malcolm, that you are also in load shedding, so I apologize for that. This is really a snapshot of how badly we really experienced generation on the grid. You could see the downward decline, and we've managed to get the most recent profile that looks like it's going up just a little bit from this year, which is quite a relief. Okay, so there was a claim that was made, which was, can water heating load remove 4 stages of load shedding, which is equivalent to 4,000 megawatts? That was a claim that was made, and so it was one of the things that really launched this particular study. Was, can we really do it? And for us, it's really, perhaps you can, but what are the consequences around it, and can we simulate both the technical and social impacts of that? The first question we really actually needed to ask was, what is the impact of residential water heating load on the national profile? And I don't think that there's any particular study that has a really good grasp on that. I think we could really say it's fairly significant, but I don't think that there's a particular study that has put numbers to it. So the study has certainly tried to do that. There's another question about why water heating load specifically, and I'll talk a little bit more about that as well. The one thing that we do probably know is that we're sitting at about 1.4, 1.2 million geysers countrywide. And so it is one of the largest contributors to peak demand. And this 5.4 number is a number that has been somewhat validated by a different research group, taking a slightly different approach to getting that number and coming to a very similar answer. So we were very satisfied with this estimation. The water heater, otherwise known as a geyser, technically we call it an electric water heater or electric resistance water heater, with heat pumps joining in as also an electric load. And typically we've got about 90% of the geysers that sit on the grid as horizontally oriented. And so that really warranted a model that could describe or characterize the loading on the horizontally oriented geyser, which I'll talk to in a moment. The majority of the geysers are resistive, as I had mentioned, and we've got a very small portion of solar water heaters, gas, and heat pumps, possibly growing, but in general, it's a very small portion. We know that the geyser is a large residential load, and I just wanted to mention it's a large load in terms of power and energy. So you've got 3 kilowatts or 2 kilowatts depending on the size, and then your energy is a significant amount, both standing losses and your usage. And the last point I want to make here is that energy storage is a flexible load. Now, if you don't know what that term means, it ultimately means that when someone wants to use the service from that appliance is not directly related to the time in which it needs to draw energy from the grid. So you could produce a delay in that, which is very useful. And we'll talk a lot more about that in a moment. I just wanted to note also that energy storage as a flexible load could be anything that has some form of storage attached to it. So a geyser is a thermal energy storage, but we've also got things like refrigerators, which is also thermal or cold storage, and batteries, so inverter batteries with PV, and even EVs. So that's why a lot of these appliances or loads are very much of interest for grid interaction. Just to talk very briefly about water as a flexible load, we've got a household that has, let's say, 3 people who live in it, or occupants that live in it. We've got a municipal electric connection, and we've got municipal water connections. These 2 connections was a very important point for us coming up with that 5.2 million number. As without these 2 connections, one can expect that this water heater would not be able to be connected. In terms of our household, we've got several loads. We've just got a bunch of plugs there to represent all of the loads. We've got the water heater, generally in horizontal orientation. And then in some cases, especially with load shedding or the advent of load shedding for a fairly long period of time, people have installed rooftop PV. The other thing I wanted to mention here, although this is not a standard household, is that you could also use an external switch, and that's where that flexible loading really can come in. So typically the water heater is controlled by a bimetallic switch, so it really looks at the temperature of the thermostat, but you could also produce an external switch to define when you allow that element to turn on. So it's 2 switching motions over here. The bottom here I've just mentioned, this switch could really be anything. It could be ripple control, so either centrally controlled by the municipality. It could just be a very simple digital or analog switch that you put on your DB board, or a fancy autonomous switch, which there are a few on the market now. So what does it mean in terms of the opportunity for power demand flexibility? So in terms of normal operation, let's say, once again, we have a house, we have 6 occupants, and we have nothing else that we're worrying about. So we just have a geyser, no external switch. This is what we could expect as one of the load profiles we would see. So these 3 trends are your temperatures. We have the top temperature at the outlet, the middle is the thermostat, and the bottom is the bottom of the tank. So it's the coldest part of the tank. These black signals over here are basically usage events from the 6 occupants. So we made certain assumptions around that. And as people use hot water, water is drawn out from the tank, and cold water comes in from the bottom. And as the thermostat sees a temperature lower than its hysteresis set point, it will start switching on the element and replenishing the energy. So these purple trends are basically the element operations on the tank. So you could see as hot water is being used in each of these instances, the temperature is dropping, and we see the energy being replenished in the tank. When we look at shifted load and we apply a switch and we say, in these gray areas, which is the Eskom peak times, we're going to inhibit the tank from replenishing its energy during these particular times, which, falls to the demand flexibility aspect of it. And this is what we ultimately see. So this is the gray area, which is the element is not allowed to turn on. And you could see that the load is now shifted to after that time is presented. All right. The other note to make is that we note that 40 degrees serviceable temperature is probably a good place to call a comfort level. So if that top temperature goes below 40 degrees, one can expect a cold shower. So in this case, luckily, it doesn't appear to be the case. All right. So just moving on to the modeling aspect. So we'll talk about the validated horizontal oriented model, and then the national population and how we've built it up for the national load. So let me just start off with a quick thought experiment. We've got vertical and horizontal tank. We've got the exact same tank. So in South Africa, we can obviously install the tank either in horizontal or vertical orientation. And we've basically got all the same elements within the tank. We've got resistive element, a thermostat, some kind of casing with insulation, and it's really just a vessel with an inlet and outlet port. This is a measurement that was made in the lab. So this is a draw event, and this is the temperatures being replenished based on that draw event along the height of the tank. So this is in vertical orientation, and you can see that as hot water is being drawn out of the tank, the element replaces energy in one large event, and then the element switches off, and you move into what's called standing losses, which is the stabilized system that just it's reached its equilibrium, and it's now just operating on standing losses. In the horizontal orientation, what we find is the thermostat and element sit in the middle of the tank. And what that means for the same volume of draw is the temperatures don't quite go in the same extremes. And when energy is replenished in the tank, there's this transient effect. And so you've got this sort of dithering of the element where it turns off for the majority of the time, but also has to turn on and off a few times before it reaches steady state. Right, and that's very important. If you start thinking about millions of geysers aggregating that load on top of each other, there's a bit of an impact. So let's talk about what that means. So that thought experiment is, what if we have 1 million geysers that have 100-liter draw? So these are 100-liter draw experiments. And we only allow them to enter or draw from the tank, from the grid within a 4-hour period. Okay. And we've randomly distributed. So we've applied a Gaussian to those draw events. In the vertical tank, this I believe was a 2 kilowatt tank. So 2 kilowatts times a million, we're getting 2 gigawatts worth of load. So these are the 4 hours of that time window. And so all of the events happen within this time window with a Gaussian applied. So you could see that's why all of these look like a Gaussian. If we did that for horizontal, so this is just this element trace being copied a few times with the exact same timings of each of the million geysers, you find that it's a significantly lower demand that comes off the exact same draws, just the different geysers in different orientations. So really, this warrants the fact that we really need a model that can describe this kind of function within a geyser, as opposed to having more traditional models where we're really looking just at the energy, which is what is mostly published in literature. So just to talk a little bit about how that was done, we had an experiment with an actual geyser, and I had access to 100 liters and 150 liters, which I used, just to show what that general experiment looked like. And this is a 100-liter draw at 8 liters per minute. So really, once again, it's just drawing water as the element reached steady state, and just watching what happens to the geyser over a 24-hour period. Okay, so that we've discussed already in some detail. The simulation, I really looked at a multi-nodal analysis, which had a bunch of layers within the tank that had heat transfer between the layers and heat transfer between the layers and the environment. I set up layers for particular layers for the element, and we've got mass coming in, so that's the inlet coming in, and the outlet, which I don't have logged over here, but it was an important point. All right, so using this particular model and tuning some variables, I've managed to get, and I will say that this is a cherry-picked result. So this is the best result that you could find, but ultimately you could see that the temperatures and the element events were fairly well matched. So we were quite happy with that. So just to talk about what we did in terms of having now this base model, and we call it a bottom-up model. So you've got this base model. It's a theoretical, or it's a model that you can validate against theory and an experiment, and ultimately add certain parameters to it to give it the variation that you would expect within in a large population. And so of that, we sort of looked at the heater model, which I've just explained. We looked at human behavior factors, which was ultimately from a study by Mayer that looked at that actually measured water usage, hot water usage from a variety of different household types. So we leaned quite strongly on that. We looked at climatic factors. The ambient temperature and inlet temperature are quite important when it comes to looking at any form of thermal energy. And then we looked at some installation factors, which we'll talk about in a moment. In general, what we did was we took a lot of these variables with a bunch of weightings, and we applied a Monte Carlo selection, so it was a probabilistic approach. We applied a random seed to it to allow for the repeatability of experiments. And just a note there that this was a very, really computationally heavy simulation. So that's where Ken really came in with the computing aspect, which we'll talk about in a moment. We took that and we generated a whole bunch of those element profiles, and we aggregated them together and ultimately produced a summer and winter national load profile. And from that, we could determine the demand, energy. We could even look at the quality of service for each of the geysers, and ultimately an ADMD. So I just wanted to talk a little bit about the study in a little bit more detail. So this is the logic which was taken place. So we took the Mayer study, which ultimately separated households in terms of house, apartment, and townhouse, and also looked at an income factor. So high density. So if you've got lots of houses in an area, it's a allegory for low income households versus the low density, which you've got this more sparse approach, and so that would be the high income group. And with that, we used some stats essay information and domestic load research information. This is all Marcus's section. And we looked at feeding that information into the water heater model. And we looked at a variety of different geyser types, given the weighted distribution within the country. And just a note there that we also considered VC 9006, which had a Class E and a Class B insulation rating on it. So basically, we've already seen a policy related to water heaters that's already taken place, and so we modelled that, knowing that there was a replacement rate to these geysers. We looked at 3 general climatic regions throughout the country, which I won't go into too much detail on. And importantly, we looked at the human behavior factors. So, as I showed you, as water is used from the tank, energy is drawn from the grid. So from that, we looked at the stochastic draw events. So that was once again a probabilistic approach. We looked at the number of occupants, and that was based strongly from the Mayer study, and ultimately the volume drawn from each of the tanks. And a note there that the volume that's drawn from the tank is highly dependent on the ambient temperature, the inlet temperature, but we ultimately move towards a 40-degree service level. So that volume drawn from the tank will change depending on what your inlet temperature looks like. Right, and then site installation factors. Pipe losses are are a big factor that could reduce some energy, particularly from a consumer perspective. And then we looked at indirect PV. So once again, we couldn't ignore the idea that because of load shedding, many households had moved towards energy security and ultimately installed their own systems at home. So we recognized that that was probably a factor to consider. I'm going to move past the interventions because we're not talking about that just yet. As part of the baseline, we generated then, given all of these variables through a Monte Carlo selection, we generated 3,000 geyser trends, which then we used a scaling factor in order to get 5.2 million for the 2023 baseline. For the forecast, we also did the same thing. So this was a baseline that if no intervention is made, we just allow the market to run as normal. The 6.4 million geysers is projected for 2033. That's in 10 years' time. Now, for the interventions, depending on the intervention, we would apply some kind of input variable, depending on what it was that we were intervening on. And we would then generate the models to produce each of the interventions. All right, I will move on to Ken Nixon to continue with the national baseline. Go for it, Ken.
Thank you, Jessie. Just thank you very much for that. And I'm going to, in essence, present the results here, but I also want to point out that the report is available. So, at your leisure, you can go and look at this information in a lot more detail. So let's have a look at what this all means. So here we have on screen the baseline curves. So I'm going to talk through these slowly. Effectively, we've got the summer profile on the left and the winter profile on the right. And for each one of them, there's some information there. So we're looking at a 24-hour window period time. And then we're looking at the demand on the y-axis here, going all the way up to 10,000 megawatt. And just to illustrate some things here, the modeling, even in the 2023 baseline case, did have a recognition that there was some indirect solar voltaic heating. So we've just put the irradiance curve there just to remind us where the sun shines. You can see, obviously, in winter, it's a little bit less. And then the main information are the two curves here. So the light blue curve, this over there, is the 2023 baseline. And in 2033, as Jessie pointed out, just based on population growth, all the modeling that has gone in, we anticipate an additional, the order of magnitude of 1 million geysers. And you can see that that has quite a strong impact, even in summer, later in the evening. On the winter curve, effectively, you can see how much of an influence the ambient temperature Jessie was talking about has on the hot water usage. There are also some things in our behavior that have changed, but going forward, when we look at interventions, we'll look at the winter cases being the more extreme. So there's some other interesting information that is included on these plots, just for information. We've got down here in the baseline, we've got what is the maximum appearing in the 24-hour period. So there we've got the value there. We've also got the after diversity maximum demand value. And we've also got a quantification of that total energy in that 24-hour period. So there's, just going to the energy figure, there's a substantial difference, an increase in the use of energy. And there's also a change in the ADMD values. On the top here, we've got the figures for the 2033 values. So just let's look at the winter ones here. What we're looking at is, based on the forecasting that we've done in the next 10 years, we're going to see an increase, significant increase to the maximum demand if we don't do anything. Hopefully that all makes good sense. Having said that, those were the values averaged over an hour interval. Now, the actual simulations that we did were per second simulations, because we always believe in higher resolution and you can always aggregate it out. Just important to note that some detail does get hidden when you start averaging what's happening in an hour. We do this on the grid. We often look at 15-minute blocks or 1 hour blocks. It's a convenient way of viewing it. But it is also useful to look at what's happening at finer resolution. So that's exactly the same curve, but this is with the higher resolution, the per minute resolution. You can see there's a little bit more fuzziness here, just representing the stochastic nature of all these different geysers switching on and off. So that was important to draw your attention to. We'll come back to that with another plot. So the next important question is, what can we do about things? Now, there's a whole lot of things that we can do. And the focus of the study was primarily at a sort of a policy and regulation intervention. So there are different things we could do. In this work, it was focusing on policy regulation, what would be practical. And just to note that whilst there are many interventions, the report didn't by any means consider all of them. And in this presentation, I'm only going to draw out one or two of them, just to highlight some things that will be quite interesting. So let's go through each of them. We're going to start with reducing the rating of the heating element. So this is the idea of reducing the size of that resistive element in as many geysers as possible. So assuming that geysers get old, they get replaced, put a policy or regulation in place that new geysers installed must have a downsized element in it. So the consideration was taking a standard 4 kilowatt element, turning it to 3 kilowatt. This is standard in a 200 liter at the moment, a 3 kilowatt down to 2, and just leaving the smaller 100 liter at 2 kilowatt. So that would be the intervention. And our prediction is you'd get through a fair amount of the fleet over a 10-year period as the geysers wear out and get replaced. So effectively, we worked around 100% adoption by 2033. This could be done by regulation and some sort of manufacturing standard. So it's a relatively painless thing to do. Talking about the sort of results, and Jesse alluded to the quality of service. So what does that mean? So we are reducing the element, but it is going to have a consequence on the quality of water that you're getting. So we can see a shift there of about 8% below the baseline, if without this intervention. So some people would have slightly cooler water. But what is quite interesting about this is there's a passive load shift that happens. Because the element is smaller, it needs to heat for longer. So effectively, you're drawing out that peak over time, which could be beneficial, especially around the peak hours in the evening. I am going to refer to, Marcus really put his finger on this. This is the notion of conservation of misery. Effectively, you've got a certain amount of hot water you need to get. If you've got a smaller element, you're going to draw out that. You just can't get rid of the fact that you need to replace that energy. And we see a little bit of benefit in the 2033 here. You can see in our modeling that we did, we assumed a certain increase in the penetration of solar voltaic systems. And you can see a bit of an effect coming through in the element curve here. So just to remind you, we've got the 2023 baseline, the 2033 baseline, and then this is the intervention, the element one there. So we can see a reduction. See a little bit of a reduction in the earlier part of the evening here, and drawing it out a little bit further into the evening, if that makes sense. This is quite a nice way of visualizing it. And effectively on the left here, what we've done is we've just done a difference between the baseline and the intervention. So effectively, by changing the heating element size, we are increasing the demand at certain periods, decreasing it at other periods, and increasing at others. I've got that the right way around. So that's a nice way of looking at these curves here. The next simple one, and remember, we're not looking at all of them by means due to time. The next one is the idea of a time of use and a sort of a time operation thing. So what we're saying here is going over the next 10 years, there would be a mechanism to install some timer switch that would effectively stop an element from switching on during the Eskom peak times, the 6 to 9 and the 5 to 9. So you can see those gray areas there. So what we did here is we didn't do anything in terms of the geyser population. We just selected a certain random percentage of them. In this modeling here, we said, well, what would happen if we had this mechanism on 10% of the geyser fleet out there? In this instance, no real impact on the baseline, the quality of service. There's this nice feature here, and I'm going to come back to it on the next graph, but effectively you can see we do have a reduction at certain periods here in the load. But there's this unintended consequence, and this is, again, that conservation of misery. We have a total loss of diversity when all of these elements now switch on at the end of that interval. Now, we haven't tried to be smart and put in stochastic. We've just said, right, at the end of that period, they all switch on. So maybe one could be more clever about how they switch on, but I think there is an important lesson here. And this is very reminiscent of what would happen at the end of load shedding when power was restored and everyone's batteries all started wanting to recharge themselves. So this year, we do have a reduction during the peak periods. We're shifting the load with a bit of a delayed peak. And what's nice in this instance is a little bit of that is being absorbed by the sort of PV systems. So there's a little bit of a reduction in energy as well. Taking it to another extreme is to say, well, what would happen if it was more than 10%? We actually had 30% with this mechanism on. This is where I think it illustrates quite clearly what that challenge is with what they call the sort of comeback load. So you've got this thing where elements have been switched off. There's now water draw activities happening in there. We need to replace that energy, and all that energy is replaced here. So I think there's a note here. If one's not careful with this, you could have quite a painful unintended consequence, a 30% adoption. I was quite surprised when we first ran this, how high that load demand is. A little bit of an impact in terms of quality of service, but definitely greater reduction. So we've gone from that all the way down there. So we've made this big difference. It's 2,000 or 3,000 megawatt, but we've got that unintended consequence. Obviously here, there's a little bit more energy saved as well. I'm near the end of this slot. We're going to just talk about the higher resolution thing, what is hidden in that averaging. And my apologies, it didn't render that line up there, but the averaging is a bit deceptive over an hourly interval. You can actually see that that peak demand there, or that maximum demand, is very, very significant. It's well over 10,000 megawatt. So I think you can see here in the per minute resolution, you can see more distinctly how that switching off happens there. The last one we wanted to talk about was an extreme one, but a bit of a thought experiment. And I think many of us have been thinking about doing this. This is the notion of what would happen if we said a certain number of water heaters didn't participate on the grid at all during peak times or even overnight. So we've taken an extreme case here. We've said between midnight to 10 o'clock in the morning, this geyser or a certain selection of the population is not allowed to draw any energy from the grid, and then again in the evening. So it's a timer switch. We only did 30% just to see what would happen. One could think of different ways of doing this. This could be incentive-based, or you're just reducing your local energy bill because you're now actually drawing it from your own PV system. On the impact there's a significant reduction in overall power demand, certainly during the peaks. A lot of energy reduction, but no surprises there. You are going to pay a price in terms of the hot water, the quality of the supply there. You are going to be dipping down below 40 degrees. And the challenge here is when you draw water in the evening here, that geyser is not allowed to switch on all the way until when the sun starts shining. And the problem is people often want to shower in the morning. So that's just the trade-off there. But we thought it'd be nice just to show. The nice thing about this is being a simulation, a model, we can play around with all sorts of different variations. So that's just a summary of what that one looks like. Effectively, massive reduction of demand overnight. So a very quick summary before Jesse concludes. Effectively, I've just taken you through some very simple scenarios. So what was interesting for me is just how many more geysers, what the population is going to be doing and what that means in terms of hot water service. We have also assumed, or based on all the modeling and predictions, forecasting, we are assuming about a 30% penetration in 2033 as being feasible and likely to happen. There's a slight increase in energy. In the instance of an intervention where we reduce the rating, it certainly decreases the peak. There's a little bit of increase in energy because you're drawing it out and you've got standing losses that need to be replaced. But this is actually a very effective passive means of reduction, a lot less complex than doing timers and interventions like that with a similar effect. We looked at the two time of use tariff and timer based type things. There's definitely a decrease in energy. There are major consequences though. This allows us to do some load shifting, but we've just reinforced the notion of this comeback load is a very big thing to watch out. And then this unusual case of just thinking about PV direct. What could we do if I don't want to pay any money for my electric water heater taking energy off the grid and I only used what's coming off from the sun? So an extreme case there. So with that, it's Jesse to do some conclusions for you.
All right, thank you, Ken. So I just wanted to turn back to the notion of, do we turn off people's geysers to keep the lights on? And can we really remove 4 stages of load shedding, which is effectively 4,000 megawatts from the grid with water heating load? And the answer for us is yes, but. And those buts are very big. One, I think particularly at the worst time of load shedding, especially when we had it running over 24 hours, I think that the opportunity to make up that comeback load becomes less of an option there for you. We can certainly reduce, and in this particular instance, we've reduced by about 2,000 megawatts. So if we have a larger portion of the population under this particular timer configuration, I think we could certainly remove 4 stages of load shedding for a short period of time, and it's absolutely not sustainable. So that's what this report tells us, and you're welcome to chat to us if you have any other ideas for simulations. The last thing I really wanted to say is what seems to be a very effective option is some form of switching on the element that is not the thermostatic switch, but rather an external switch. And there are a few ways, like I said, that we use it. The municipality option is through ripple control. Unfortunately, it is a bit of a one-way street, so the municipality decides when to turn on and off the geyser, and sometimes if there's a faulty switch, people have a cold shower, call a plumber, and ultimately disconnect from the system. As a user, you could take control of it and really just put a switch into your DB board yourself and make whatever controls that you want. And we showed that if you have a PV system on top of this type of switching, you could do quite a lot with it. And then, of course, there are these autonomous controllers that are out there. So certainly we're moving to a space of smart grids, smart controllers, autonomous control, etc. And so there's really a space for that to work with what we call a flexible load, which is something that obviously has a storage component to it. So that's everything. This is just a few details about the project. I see that the report has been shared. So we just want to thank you for your attention on this, and we're happy to take any questions. Thank you.
Thank you, Jess and Ken. Much appreciated. Very nice treatment of the topic. Okay, folks, we've got, I think, 8 minutes to handle questions. Floor is open. Guys in the audience, the report link has been posted. If you want to get it from the horse's mouth now, please pass your questions. I'm standing by. Thank you. Wayne, go ahead.
Yeah, thank you, Jesse and Ken. Thank you. It was really interesting. Have you, in your research, have you looked at all at the large-scale DSM ripple relay rollouts that Eskom did in the sort of mid to late 2000s? Because, yeah, I know at the time they had the suppliers of the technology advocated dividing the ripple relays into groups so that then they can be individually the groups can be individually addressed, and then you reduce your comeback load at the end. Have you come across that, or did you consider, can your model handle that kind of scenario?
Yes, thank you, Wayne, for that question. Absolutely. So the ripple control was one of the scenarios that we did consider. We just didn't put it in this because the results are not as flashy as these ones. But yes, absolutely. So you're rotating a group of geysers to switch them off and then return them back into the grid. So you reduce that comeback load significantly. So yes, absolutely, we did do that.
If I could just add in, obviously, when you reduce the customer groups to cohorts almost, then your level of participating in any one state is obviously divided by the number of cohorts that you have. So, as Jess said, results less flashy. Thanks. Any further comment from you, Wayne?
Sorry, this is just it's a bit of a pet interest of mine because I was involved with it in my days at Nelson Mandela Bay Municipality. Another question I've had was, but it will mean a change in the technology. It's if how possible it would be to not overheat, but to heat the geyser to a higher temperature using PV, so that you can actually have less of a discomfort level when you switch off for longer periods of time. But obviously, then the thermostats will have to be switched to a higher temperature, or you replace the thermostat with some kind of a smart box. See, Ken was nodding. So, any developments in that field?
Ken, go for it.
Well, I mean, it's just to say, absolutely, it makes sense to do these things. The focus that we were looking at was really the regulatory and the policy thing, but we've got a model that we can do all of these things and see what happens. The challenge with that overheating is that you do need a little bit of a better mixer on the end, so it's a little bit more invasive in terms of its effectiveness. Because if you've got a variable temperature coming out of the tap, you can have some surprises there. But so certainly possible. Certainly something we can model and simulate, and I think there is a lot of merit. On the flip side, that applies just as much. We've focused on water heating here, but this also applies to refrigeration. So you could also do the same thing in the opposite direction. So these are all exciting things, but they do lean a little bit more on technical implications and rollout kind of issues, if that makes sense.
Thanks, Ken. Lloyd, I see you've got a hand up, and then after you, Malcolm, go ahead, please.
Yes, thank you, Marcus. Good afternoon, everyone. Thank you very much, Ken and Jesse, for the very inspiring presentation. And I've just downloaded the report. Yes, it's going to be a wonderful read for me. And I think it will form also a good base for some of the research that we are also doing. Just a quick question out of interest there. You know, with the price of electricity going up, I've seen many customers resorting to switching off the geyser. You know, when they go to work, they switch it off for that number of hours and then switch it back on when they come back as an effort, you know, to save electricity, so to speak, and therefore, as a result, cut off the price of obviously the cost of electricity price. Now, have you done any simulation around that to look at number one, how does it affect the lifespan of the geyser itself by switching it, instead of the geyser naturally switching off and off through a thermostat? Now you switch it off, you know, at the circuit breaker. And the second question is, have you also done some simulation to look at really how does it affect the load profile, not only for that one customer, but if you were to extrapolate it to that number of consumers, probably maybe 30% of that big number that you are showing us? Thank you.
Thank you, Lloyd. Yes, absolutely. We've had all these same discussions in our technical meetings. Lloyd, to address your first question, we certainly acknowledge that this is common practice within South Africa. The challenge with trying to model that is we simply don't have the information. So what are the schedules that people are using? We don't have a study to draw on. So if you're aware of any data that we could use to put into our models, we'd be very happy to try that out. So that's the one challenge is that we just didn't have the user data available for what kind of switching, and I think everyone has their own way of doing it. So if we could find the trends around that, it would be very useful for a simulation. Your second question is what that means for the life of the geyser, and in all honesty, it has no difference. It's really just your circuit breaker that's going to experience wear and tear. So the geyser itself, there is absolutely nothing about that wears it out. The thing, interestingly enough, affects geyser life is this thing called a sacrificial anode that no one replaces, and so within every 5 years, geysers tend to the chemical content in the water eats away at the lining of the tanks, and so that's the reason why geysers burst. It's not usually a thermostat failure. And then the last question that you had was how does that affect the load profile? And once again, it links to my first answer, which is if we have an idea of what those user schedules look like, we could try and simulate it for sure.
Marcus, can I just come in there as well?
Yes, please, Ken.
So, I mean, the fact that someone is switching off the geyser there is a saving of energy, but it's not that much. The only energy saving that you're getting, and Jesse, you must pull out the numbers for me. I don't have it at my fingertip. All you're saving is those standing losses. So those little replacement, you remember Jesse showed you that curve? You've got the bulk energy, and then you've got these little things. And with these modern Class B geysers, those standing losses are not that big. If I remember, Jesse's about 20 Rand a month, or am I totally off the mark in terms of?
It's around 2 point something kilowatt hours per day, depending on your standing losses. Yeah.
Okay, so it's a little bit more than 20, but I mean, so there is an energy saving, but it's not as big as one would hope it would be.
No, 60 units a month. Thanks.
60 units. Thanks, Marcus.
Yeah. Thank you, Ken. If we can go to Malcolm, this is probably going to be the last question. Malcolm, you're welcome to come in.
Thanks a lot. Yes, so just to go back to that thing of the savings, we did a number of tests on that, and we found very, very small savings on switching off and switching on. Where it does make a difference is if you've got people who, especially in winter, where you putting a lot of cold water, using hot water, running hot water into a sink, washing dishes or something like that. So you're getting cold water and it's heating up, cold water and it's heating up, cold water and it's heating up. Not at shower times. So that was the biggest move. I'll get to the question now. The interesting thing on your 10-3 usage, did you look at the national demand for electricity? So, on that last one that you said you're going to go to use the PV Direct, just as a matter of interest, the 10-3 period, that tends to be your highest peak, where you think it's morning or evening, but overall, and I find it with a house that we are running and testing, and 2 o'clock in the afternoon is the highest time, and that CSRR is giving us exactly the same numbers. So you change that around. But at the same house, what was interesting, and I want to get back to that geyser using the peak, the very hot water for electricity, using PV to get your water high. At the test house that we've got, we actually run 3 geysers or 3 water heaters, and we use 2 of them for your heating. And the the PV heater goes up into the 80s. We actually have to put a shutter across it because it gets too hot at peak time. And then we feed that into the middle geyser, which we use for showering. And that one's got an element in it. But we're not getting very good results on it. So instead of doing it within 1 unit, using 2 units. But the one is just, we have a problem feeling too hot. But it is the other way, is to preheat one and we put it into the other one, rather than putting it all into one. Yeah, very interesting. But thanks so much. This was awesome. It really fits in with what we're doing, and it's exciting.
Thank you, Malcolm. It would be really good to see the results of your work on the way. If you need a place to table it, please consider us.
Will do. So we're still doing a lot of work on it, and we're trying to do some optimization. I'm working with the University of Missouri.
Okay.
So,
thank you very much. One person here, which is possibly a piece of the jigsaw puzzle, is Maputi and GLS. Maputi, can you confirm you do or don't have access to? I know GLS is partially into water flow and water network design. Do you, by any chance, have any specialization in hot water usage? Okay, I have no response from Maputi. Thanks. Okay, folks. Thanks from my side. Thanks very much to Jess and to Ken for popping in to present the results of this research. For me, it has been very interesting in perhaps shedding light on how people use hot water in South Africa, and understanding what the impact of that is, and perhaps understanding the impact of some of the simple things that can be done and some of the more complex things that can be done. But we did hint at the preloading of geysers, partially, I think, with the words of Wayne, and that is also an area for further investigation. IoT and other control mechanisms to preload geysers so that they are actually at sufficient temperature before the evening peak, and so they can be cut off during the peak. Okay, from my side, thank you everyone for sitting in, and thank you to Ken and Jess again for presenting here. It is much appreciated, and if there is any movement on this, we would love to see the developments.
Thank you, everyone, for the opportunity. Bye.
Thanks all.
Thank you. Thanks to the Load Research Chapter members. We will close off now. I see you getting a clapping of hands to the presenters. Much appreciated again, and I will close off the meeting. Thanks so much.